Well, hey everyone. So a real pleasure to welcome Chris Bretherton today. So Chris is the Senior Director of Climate Modeling at the Allen Institute for Climate, and he leads a research group there that's using machine learning to improve climate models, collaborating with NOAA's GFDL laboratory. Chris has been had a illustrious academic career since 1985 to 2021 as a professor at the University of Washington. He's an expert on cloud formation, turbulence, and cloud climate feedbacks, how to represent clouds better in climate and weather models. He's received many accolades, including being an IPCC Fifth Assessment Report lead author in 2013, receiver of the Jules Charny Award. He's a fellow of the AMS and AGU, member of the National Academy of Sciences and the Washington State Academy. He's also a wonderful human being, a passionate, considerate educator and mentor of even very junior mentees. I can attest from personal experience, and enthusiastic, creative, inspiring collaborator, all around great person. And so I'm honored to have him as a friend and colleague as well. And so he's got very interesting thoughts on the future of machine learning and climate science and has since its beginning. So we're really excited to have you here, Chris, and looking forward to your talk.
Okay, well, thanks very much for the kind introduction, Mike. And also thanks to Pierre, who's in France, and Jihe for inviting me to speak in this series. Let me start by sharing my screen then. Okay. Hopefully everyone can see my screen now. Mike, is that the case?
Looks good.
Okay, great. So I'd like to talk about a project that we've had for the last 3 years to try and improve climate models using machine learning. In particular, our style of machine learning that we were working on is what we call corrective machine learning. But in the end, I'd like to compare this with a number of other approaches out there for emulating more accurate climate models or data sets with the purpose of basically making fast climate models that can more accurately represent both the climatological mean and extremes and how they are going to change under global warming. This isn't my work. This is the work of a group that I direct at AI2, shown here. And we also have now 2 external partners. Our long-term partner has been NOAA GFDL, in particular, Lucas Harris's weather group at GFDL. And we've also recently begun to work with Lawrence Livermore Labs under a project directed by Peter Caldwell. All of our work is open source, so our code is available via a GitHub site. We have a web page that I'll at the Allen Institute for Artificial Intelligence, AI2. So what I'd like to do is start by sort of introducing what the problem is and why machine learning is an appropriate strategy. Then talk a little bit about our own approach to machine learning, or at least one of our approaches over the last 3 years. And then like to spend a little bit of time at the end in a more prospective view of where the field is right now and where we as a group are trying to go next. But I think in order to appreciate this problem, you should realize, okay, well, what are we doing right now? What's the architecture of traditional weather and climate models for the last 50 years? And in particular, a weather model is typically then a model where we try and represent equations of motion and all of the other physical processes that we think are important for simulating the atmosphere. And so we integrate that model forward in time on a discrete grid of points. So this is then frequently used to simulate the weather up to 10 days or a couple weeks in advance, after which the weather is no longer deterministically predictable. But if you integrate a model like that longer, coupled appropriately to land, ocean, and sea ice, I can run indefinitely and basically produce a climate simulation. And in fact, climate models, as we use them today from major climate model development groups, the atmospheric component of those is in fact such a global weather simulator. So the spacing of the points on that grid depends on how long the simulation is going to be. It's computationally limited. So for weather forecasting, typically we might try and use a grid spacing of as little as 10 kilometers and up to 150 vertical levels. For climate, where we have to integrate for centuries, we might use a grid spacing of 100 or 200 kilometers and fewer vertical levels. The atmosphere is a fluid, so it moves things around. So the things that we need to predict are the temperature, species of moisture, so water vapor, cloud water, ice, precipitation, and the winds that blow these things around. Plus a lot of other trace species we're often interested in, things like chemical compounds or aerosols. A weather or climate model consists of airflow solver, often called the dynamical core, which just discretizes the equations of fluid motion and represents them on a sphere. And in addition, what we call physical parameterizations, which are basically human-designed representations of the effects of clouds, precipitation, radiation from the sun, and long-wave infrared radiation from the Earth and the atmosphere, of interaction of the atmosphere and the land surface. All of these things then are represented in each grid cell. The physical parameterizations are designed from physical principles, but ultimately they're expert. There's a fair amount of expert judgment and input that goes into them, so they're subjective. Usually, but they don't have to be, physical parameterizations work column-wise, so they make predictions about changes in each column from inputs of the temperature and moisture profiles and wind profiles within that column. They can be stochastic. Subgrid variability is one of the things we try and represent with such parameterization. So this means everything that we don't know about a variable, like where clouds are, where mountains are within a grid cell of the climate model. This is particularly challenging to represent. It's essentially a statistical problem, but often not very well posed and with many dimensions of variability. We could get away from representing subgrid variability using a finer grid, but it's important to appreciate that if we were to make the grid spacing of a weather or climate model 10 times finer, it would require about 1,000 times the computation. So you can quickly exceed our computational power. So it's fair to say that right now, this kind of model is rate limited by our computational capabilities and also the electrical energy that's required to make them. Now, well, what's the problem with what we do right now? Well, in climate modeling, there are many things that are actually very well predicted by climate models, but there are uncertainties, and some things are more uncertain than others. And one of the important uncertainties in climate models has to do with predicting trends in the means and extremes of regional precipitation. So this slide shows an example of that. So on the left, then, we can look at temperature change in degrees Fahrenheit predicted by a set of climate models in light gray lines, both over the historical period and then over a future scenario where greenhouse gases are then rapidly increasing, sort of a business as usual type scenario. And what's shown here is decadal averages from the models, along with a dark solid line, which shows the observed decadal averages from the 20th century. And what you see for temperature is all models predict the temperature will go up substantially over the next century. All models are fairly consistent with the historical records, because if they weren't, people would have tuned them to do otherwise. But there is some variability. The variability is actually substantial, but from a policy point of view, the important thing to know is it's going to get a lot hotter over this region, according to all climate models. This region, in this case, being the Pacific Northwestern United States. Now, if we look at precipitation, what we can see is that the same models don't predict much precipitation trend over the 20th century. And in fact, the observations show no clear trend and just a lot of variability. But over the 21st century, some of the models predict a significant precipitation increase. And then another group of models predict a slight precipitation decrease over this region. And this is a region that relies on water for hydropower, for agriculture, for water use for cities, and so on. And so the difference between these two classes of scenarios is actually very important for planning purposes, for infrastructure and other planning. So local precipitation trends are harder to predict than temperature, and that matters. And it doesn't just matter for means, but this also reflects itself in extremes, things like droughts and forest fires, or in extreme flooding. Okay, so this was one of the motivations which led the estate of Paul Allen, co-founder of Microsoft, after his passing, to start a philanthropic climate modeling effort at his holding company Vulcan in 2019. Initially, that had two groups, a group that was basically trying to make the finest grid models we can make of the atmosphere, so-called global storm resolving models, run faster on modern computing infrastructure. That project ran 3 years. It's finished now, although it's had some successes and has been taken over in part by NOAA. And a machine learning group, which is what I direct, whose goal is to make coarse-grid climate models, which we can run relatively quickly, better, more skillful, using reference data sets, for instance, very fine grid models like the one that the DSL group was trying to make faster. So the goal is, the point is then, is that a fine grid model maybe is more reliable for predicting climate and climate change than the coarse grid model, and therefore emulating the fine grid model with the coarse grid model will make the coarse grid model therefore a more reliable tool for looking at climate change. The aspirational goal of this was, in fact, to have climate model uncertainty about regional precipitation trends in the 21st century compared to the current uncertainties in the CMIP6 models. For this project, we initially partnered with NOAA GFDL in Princeton, because they already had a 3-kilometer grid, horizontal grid, global atmospheric model called the FE3GFS that's basically based off of our national weather forecast model, which is typically run at 13-kilometer resolution, a coarser resolution. And they are also climate labs, so potentially they would be interested in the results as well as providing data for our project. In 2021, our end of the project moved to the Allen Institute for Artificial Intelligence, AI2, which is a nonprofit AI institute in Seattle, also supported by the Allen estate. So in addition to the collaborations we now have with climate modeling centers, we're actually also collaborating with other R&D groups, for instance, Mike Pritchard's group at NVIDIA. So our group started with some somewhat unique characteristics. So we started primarily as domain scientists who knew something about machine learning without being real expert. So the perspective that we took then was that of wanting the things that domain scientists want. So we wanted to develop machine learning that fits flexibly into existing climate models. There's a huge amount of human effort that's gone into developing climate models. And although it would be nice to make revolutionary change, a way to make evolutionary change is to build tools that can slot into what they have already done without completely making what they've done no longer useful. We also wanted to make sure to develop machine learning that respects the physics that we know, the conservation of air mass, heat, moisture, and momentum. This helps it be interpretable. The machine learning should also be adaptable to different climate model formulations. We wanted to focus on uncertain aspects of climate models. So for instance, the flow solver of climate models is pretty certain what equations we're trying to represent, and there are well-defined techniques for doing that. The physical parameterizations are not so certain. And then the strategy we took was to train a coarse-grid climate model to efficiently emulate a fine-grid climate model. That was kind of the design philosophy. And it's important to recognize that we were interested from the start in trying to do machine learning that would help, that would actually help climate models with the problem they have, which is the real atmosphere as opposed to idealized problems. So we were not working primarily on toy problems, but we were starting at the other end of, okay, we have the real atmosphere, what can we do with machine learning for that? And when we started, the state of the art was a lot different than it is right now. It was relatively simple. We had deep neural nets, convolutional neural nets, long and short-term memory systems, and random forest-based methods. And there's been a huge amount that's changed since then, but it's important to appreciate that when we started, there wasn't a lot going on yet. So our approach is then relatively simple-minded, I guess I would say, from the machine learning point of view, but it has the advantage of being relatively easy to understand. So on the left is a coarse-grid climate model. So white is clouds, green is precipitation. You can see that there's a relatively discrete characteristic because the grid spacing is 50 kilometers in the example I'm showing you. On the right is a 3-kilometer simulation using the GFDL version of FE3GFS. The cloud fields look a lot more realistic. You can see things like typhoons in the Pacific. And basically then the goal is to train corrective machine learning to make the temperature, humidity, and winds of the coarse model on the left track a reference model like the one on the right. So we'll treat what's going on the right as being the truth, even though we know a high resolution model also will have biases. And the way that we chose to do that was using what's called nudging. So basically, we continuously force the climate model on the left as it's evolving to match the evolution of the model on the right by Newtonian relaxation with a 3-hour relaxation timescale. And the actual tendencies required to do that, we call the nudging tendencies, and they are what we machine learn. If we could machine learn them perfectly, we could add them back to the climate model at the left, and we would get the evolution of the model at the right. Of course, we can't learn them perfectly, so this doesn't work quite that well. The nudging tendencies are interpreted as a needed correction to the physical parameterizations, since we regard the dynamics of the model as being comparatively accurate. However, there is actually also an aspect of this that's correcting the coarse grid dynamics to the fine grid dynamics, which don't have as much discretization error. Now, because our machine learning is a correction, then when we actually use it after we've trained it in this full model, it's interacting with other model components, in particular the fluid dynamics and the physical parameterizations of the coarse model. And so that means that we are running it, we're testing it, if you want, in a different context than we're training it, where those other components are known. And so as a result, offline skill does not guarantee online skill. In fact, offline skill may still lead to a machine learning parameterization which doesn't produce stable simulations. If you can make it be stable, it may not produce accurate weather forecasts. Even if you can make accurate weather forecasts, it may start drifting over time and produce climate bias. So you have to climb this pyramid of online skill to where we get both accurate weather and accurate long-term climate, which is going to be the mean statistics of that weather. So another important aspect of this is how we actually do this. So we have a sort of a two-pronged approach. The reference simulations, the 3-kilometer simulations, are actually run at GFDL on their high-performance computing system, Gaia. And they are coarse-grained, so reduced in resolution from 3 to 25 kilometers online. And that reduces the data volume enough so that we can store them every 3 hours and move them to Google Cloud, even if we store a year or more of data. Once this data is on Google Cloud, then we do all of our other work on machine learning work and the Fortran simulations using FP3 GFS on the cloud. So we do this within Docker. And what we do is we wrap the Fortran FP3 GFS model, run at 200-kilometer resolution in Python, so that we can add machine learning components and extract what we need to from the model. And then all the machine learning is done with Python tools like PyTorch. If we if we look at the initial architecture that we used, it was pretty simple. So we started by using random forests for our machine learning. We started with, as our reference data set, not using a climate model, but instead using reanalysis. So reanalysis has the advantage that it's data-driven. It's an estimate of the real world, available on a global grid for many years, 40 years, but it doesn't include long-term climate change. So can't really use the machine learning you get from this for climate change simulation, but it is a pretty important proof of concept. So here, since we're doing column-oriented machine learning, our input features are the vertical profiles of air temperature and specific humidity, along with some additional things like the surface height, the sea surface temperature, the insolation, which are also important scalar determinants of what we expect the physics-based or the physics-derived tendencies are going to be. So what we're predicting then is a heating and moistening profile. So and the predictions are then trained on these nudging tendencies. Now, it's important to appreciate that the errors in our base Fortran model are actually pretty substantial. So if you run the Fortran model at 200 kilometers, it actually produces not too bad a climate. But what it does to do that is it initially drifts moist away from the conditions of the real atmosphere until it starts raining enough to make a balance between evaporation from the surface and the amount of precipitation that falls from the sky. And if you instead just confront it with the real world state of temperature and moisture, initially then it precipitates too little. And not just a little bit too little, but almost 40% too little. And so if the goal of your machine learning is to keep that atmospheric state close to the observed time evolving atmospheric state, it actually has to get rid of moisture to make up for the fact that the model isn't precipitating enough. And so this is what we call a drying tendency. And in column integral, then the drying tendency is the precipitation the machine learning has to make up that the physics isn't doing to keep the atmosphere in its real observed state. And so on the left is the time mean of this column drying tendency, shown as a map. So blue indicates regions where there is needed drying. Red indicates the very small number of regions where there's slight additional moistening needed by the machine learning. And on the right is the machine learning prediction. So here I'm showing the time mean prediction from the machine learning. And you can see in time mean, the machine learning is doing exactly the right thing. It's drying the atmosphere by the right amount in the right places. Instantaneously, it doesn't do as good a job. And instantaneously, the nudging tendencies are actually quite noisy, and it only predicts 10 to 30% of the variance. So if we look at the corrective tendencies that the machine learning is producing and compare them to the physics tendencies, it's interesting to see the differences. So the physics tendencies in column integral of moisture, so this is red indicates regions where there's the physical parameterizations of moistening, and blue indicates drying. You can see that there's a mixture of smooth patterns and very sharp patterns. The smooth patterns are due to evaporation from the surface. The blue patterns, the very sharp patterns, are where the physics parameterizations are predicting precipitation. And mainly that's in the tropics, where there are organized thunderstorm systems that are parameterized using the so-called convective parameterization, which has a tendency to flicker on and off. So those are these blue regions. And so at this particular time then, those are very sharp. And then the corrective tendencies from the machine learning shown in the middle, they're on a scale that's only half as large. So that is kind of exaggerating them a bit. But the main thing you can see is they're much smoother functions of state. So it can, they have a slightly different character than the physics tendencies. You add these together, and this would be the total drying that the model does in a given time step to try and keep the coarse model on the rails so that it evolves like the reanalysis data that it's trying to train to reanalyze. Okay, well, so how well does this approach work? Does the machine learning actually help? The answer is yes, it does help quite a bit. So if you, for instance, try and make forecasts with the baseline 200-kilometer model and compare that to what happens if you you add the machine learning corrections to that baseline model, and you ask what the error looks like. Error is on the vertical scale to the left, and this is error in surface pressure. Root mean squared error of the pattern of surface pressure as a function of the time into the forecast that starts very close to 0. And then the error saturates at no forecast skill after about 10 days. What you see is that the machine learning corrected model is always under the baseline model. So that means that it gets to a given error about a day later than the baseline model. You've added about a day of forecast skill, which is pretty significant in weather forecasting. In addition, if you look at the time mean patterns of the precipitation bias over a year, and these are time mean biases relative to actual observed precipitation, independently derived from a different data set. The RMSE here, which is the mean squared pattern error, is about 25% less in the machine learning corrected simulation than in the original 200-kilometer model. And in particular, the ML correction helps a lot over the Himalayas and over Africa, and sort of more subtly in a variety of other regions. Now, that was using reanalysis as a reference. And we wanted to move on to using a fine grid model as a reference. And the real reason for doing this is that we can run this fine grid model in multiple climates. We can warm the climate up, run the fine grid model again, take training data over a variety of climates so that our machine learning correction can perhaps work over the whole range of climates we might want to simulate with a coarse resolution model, and therefore work for climate change simulation. So one question is whether the fine grid model is actually any better. I mean, it makes pretty looking simulations, but what about numbers? So one way we can test that is we can compare time mean precipitation patterns from the fine grid simulation shown at left with 3 kilometer horizontal resolution, the coarse grid simulation shown at right, which has the 200 kilometer resolution. And here, blue indicates dry biases, red indicates moist biases over the averaging period. And what you can see is that the fine grid model is in fact doing a lot better job, at least over land is shown here, than the coarse grid model. The biases are on average about half as large, which is a big improvement. The reason that this works so much better is that the fine grid model is explicitly simulating cumulonimbus clouds, which the coarse grid model has to parameterize with its cumulus parameterization. And the topography of the Earth is much better resolved at 3 kilometers than 200 kilometers. In addition, it resolves other variability, like in clouds, that requires subgrid parameterization in GCMs. So not only is the fine grid model, not only is it more accurate, but it's more accurate for a reason, which is that it actually is a fundamentally better simulation with fundamentally less assumptions needed about how the atmosphere behaves, because there's less subgrid variability that we have to represent by parameterization. We can't run the 3 kilometer model forever, but we can do simulations of a couple of years with it, including in multiple climates. Okay, so now how do we apply machine learning in this context? So in our initial application, we only had a 40-day run to train on. So we only tried to train and test on single seasons. We have to coarse grain the model output from that 3 kilometer grid to the coarse resolution, 200 kilometers. We partly do that online, and then we do part of the coarsening offline from 25 to 200 kilometers. And we have coarse model output every 15 minutes. We then use this as the training data to nudge the coarse model toward the fine model over those 40 days. Machine learn the nudging tendencies as a function of the coarse model state in each column. And then we apply that on prognostically as a correction to the 200 kilometer model. When we did this, we were upping our game slightly in terms of machine learning. So in addition to random forests, we used shallow neural nets for this, or moderately shallow neural nets. And we actually also, in addition to learning profiles of the temperature and moisture changes from the nudging, we also learned we machine learned the surface downward radiation, because this helps the land surface to not drift as well. This slide here shows a snapshot which shows something I mentioned earlier, which is that there's a lot that's very hard to learn about these nudging tendencies. So this is at one particular time. It's a north-south slice through the depth of the atmosphere. So 1,000 hectopascals is the bottom, 200 hectopascals is close to the top of the atmosphere. And it's a slice along the Greenwich meridian, so you're actually looking through Africa. So you're seeing from the south slope of Africa at 8 degrees north So the Atlas Mountains, or some mountains on the north side, at 30-some degrees north. And what's shown here is the nudging tendencies of specific humidity. And blue indicates drying, red indicates moistening. And what you see on the left then is the actual values. And for this particular time, this is what the machine learning predictions of these nudging tendencies were. And this is a time that wasn't part of the training data set. It's just a random time from the testing data set. What you see is actually both of these approaches capture almost the same information about the nudging tendencies, which is reassuring, but less reassuring. It's not at all of the variance that's there, capturing maybe 10% of the humidity tendency shown at left. So this shows that there's a lot that this machine learning is missing. Nevertheless, it does help a lot again. So like with the reanalysis trained machine learning, we are able to do a lot better in terms of the pattern errors of time mean precipitation over land, 30% better, versus where now the errors are measured with respect to the fine grid reference as opposed to the observations, because the fine grid reference is what we were training our coarse resolution model to emulate. In addition, and importantly, the original data set had a large moist bias in precipitation over land. So that's the gray bar shown at the left, showing that the mean bias in precipitation in the original baseline model was over 1 millimeter per day. So it's precipitating too much in this case. Too little before, but now too much in this case. While both of the forms of machine learning largely get rid of that bias. Lastly, you can look at the diurnal cycle of precipitation over land, which is a classic problem area for climate models, which tend to put a peak in precipitation over tropical land in the morning hours, when in reality it's observed to be in the evening. And here the solid dashed line is the target. It's the diurnal cycle from our fine grid model. And the baseline run with no machine learning is the solid black line. You can see it actually has a diurnal cycle with sort of the right phase, but it's way too small in amplitude, as well as having a large high bias. And then the machine learning schemes are shown in the orange and blue. And looking at the neural net, which is our favorite scheme, but they both look pretty similar, they do get the right amplitude of the diurnal cycle, which is a hard thing to do. They still actually, interestingly, have a little bit of an early bias in the precipitation of about 3 hours, about half as large as other models would have. Then another thing we wanted to see is, well, okay, if you run the climate model with this machine learning for a longer period of time, is it stable? Does it drift? And we couldn't do this with a 40-day data set. We had to wait until we had a 1-year simulation with a 3-kilometer model that covers the entire annual cycle, so we could machine learn around the entire annual cycle. But again, we machine learned corrective tendencies to temperature and moisture, and then used them in this context. And we found that depending on the random seed that we used, we got varying qualities of results. After a while, all of our results did represent improvements in the precipitation climatology to differing extents. The plot at the left shows 4 different seeds plus the ensemble mean of those seeds applied as machine learning corrections, and shows the time mean precipitation error relative to the fine grid reference in 4 seasons. And so that's the dashed line. The dashed line indicates the baseline model. So with no machine learning correction, what its errors would have been. And the other lines then show the errors with each of the machine learning corrections added to it. And one of the seeds actually improves the precipitation climatology by 20% in all seasons. The other ones do a little less well. They all do a little better than the original baseline. So if we take that best seed, and now we try and run the model out for multiple years with a repeating cycle of sea surface temperature and ask, is the model still stable with the machine learning correction? That's the curve in green shown on the plot at the right. So we ran it out 5 years and looked at the annual mean precipitation. You can see the annual mean precipitation, the global mean precipitation. See the global mean precipitation has an annual cycle that stays pretty fixed with some natural variability and roughly matches that in the fine grid reference shown for the 1 year that we have it in the black. While the baseline model is biased high over that year. So the machine learning is also able to be run stably indefinitely. Okay, well, so with that, then now we can go to final step here, which is let's try this and train the corrective machine learning across multiple climates. Now here we did not have 3-kilometer simulations for all the climates that we want at the time we were doing this. So instead, what we did is we used a 25-kilometer version of our FE3 GFS model as the fine grid reference and a 200-kilometer model as the coarse-grid. So there's actually a little bit less to learn because the 25-kilometer model and 200-kilometer model are less different from each other than the 3-kilometer and 200-kilometer model simulations. But now what we did is we ran 25-kilometer simulations with sea surface temperatures. We unfortunately don't have the ability to ocean couple this model yet. With sea surface temperatures reduced by 4 degrees, unperturbed, and increased by 4 and 8 degrees. Learn nudging tendencies in all of those climates, simultaneously trained on all of those 4 climates, and then applied this one set of nudging tendencies to new simulations run in all 4 of those climates with 200-kilometer resolution. So we can compare that to a baseline 200-kilometer simulation of all of those models. And now we're using the 25-kilometer as the reference by which we measure errors. And so now we have reference simulations in all 4 climates. So you see 4 sets of errors. And here the yellow is the baseline simulations with no machine learning. And the red is what happens, or pink is what happens if we add the machine learning corrections in each of the climates. And what's shown here is precipitation pattern error, RMSE, annual mean of annual mean precipitation is the left one of those 2 plots. And the bias average of precipitation averaged over all land areas is shown on the right. You can see the machine learning is able to remove the bias almost completely, which is really nice, that the mean land bias. It reduces the pattern errors of precipitation quite a bit, especially in the colder climates. And it improves it somewhat in all of the climates. So great. So this actually can work across multiple climates. And so we could use it for climate change. And we can do an out-of-sample test similar to one that I think Mike and others have done in past work, where we look at intermediate climates. So we can, for instance, take our 25-kilometer model and gradually ramp up the sea surface temperature from present day by 1 degree per year for 4 years. And so then the question is, does our corrective machine learning, which was not trained on the intermediate SSTs, only the 0 and 4K, does it reduce the pattern biases throughout this ramp simulation? And the answer shown on the right, if you look at the annual means over the 4 years of ramping, so this kind of spans the intermediate climates if you want, in every single one of the years, the pattern error of precipitation is reduced by about 20%, and also the biases of surface temperature over land are reduced on the same order. So, so this works across a range of climates for climate change simulation. Now, so that's where we got to last year. Let's just talk a little bit about a couple of more recent developments before going on to the prospective look. So we've actually further been able to reduce our biases of the machine learning correction by also using machine learning corrections to the wind tendencies. Initially, we weren't able to do this for this when we nudged a fine grid to a fine grid reference. And it turns out that was because we were inserting the corrective wind tendencies upside down. So with the top of the model equal replaced by the bottom. And so that implementation error, which had a very, actually was very understandable given the structure of FE3 GFS, basically made it impossible to use the wind corrections. But after we fixed that, which we discovered by accident, suddenly we could use wind corrections, and they actually further improved our results. And so in particular, we're now able to reduce annual mean pattern biases of surface temperature by over 50%, and surface precipitation by 30% or more, compared to a actually better baseline than we originally had. So now we're really getting down to quite nice small pattern errors in the fields. But I would say it's still the case that we can't perfectly emulate our fine grid model. Our biases in doing that are, half as large as the model with no machine learning, but they're not 10% as large. So that's okay, but not totally satisfying. Another interesting thing, I mentioned before that different random seeds can, yield slightly different machine learning, and they all work roughly the same for forecasts. But the further you get away from the forecast setting on which the machine learning is trained, it's trained basically to remove nudging tendencies, if you want, which is basically equivalent to trying to optimize a 3-hour forecast. We're hoping that a better forecast leads to a better climate, but it doesn't exactly. And so, as I mentioned before, some seeds lead to lower climate biases. And so in particular, this is one more example of how that works. So what's shown here is the precipitable water field, the column humidity field, and what's shown are biases relative to the mean, and this is the zonal mean of that, so the latitude mean of that. So the way you read these plots is latitude is the vertical axis and time is the horizontal axis, and we're looking over a period of about 3.5 months here. And so red and blue indicate developing biases in different simulations. So the baseline simulation with no machine learning drifts away from the fine grid reference almost immediately and develops some dry and moist biases shown in the left panel. And if you look at our best seed, seed 3, that's the right panel, the one in the middle here, you see it develops precipitable water biases, which are actually no larger than the baseline. They actually have a fairly similar character to the baseline simulation. And precipitable water is one of the fields we have the hardest time with. On the other hand, another seed, seed 0, clearly develops much larger moist biases in the subtropics. So if you look at the precipitable water root mean squared error, the pattern biases averaged over, I think this was a year. Seed 0 has a very high pattern bias, much larger than the baseline in red, and seed 3 has a lower pattern error than baseline shown in the red. So this is a little bit disturbing, right? Because all of these models are trained on the same data using the same protocol. You don't really want them to be as different as this. And it turns out that some of this difference seems to be associated with the machine learning going out of sample. So basically, the problem is, we train our machine learning on nudging tendencies, which come from reference simulations, which have a particular climate. And if the climate is different than that, then it's possible that the machine learned tendencies are no longer reliable. So one thing you can do, and this was work of an intern at Columbia, Clayton Sanford, and we're still working with him to get this finally published, is to try and detect if the temperature and moisture profiles go out of sample. And we can do this using something called a one-class support vector machine approach. And if the atmospheric profile in a particular column goes out of sample, we just turn off the correction because we regard it as unreliable. Now, the novelty detector we use is actually pretty strict and rejects data perhaps that it shouldn't. Turns out that seems to work better for some reason. But if you do this, it not only keeps the machine learning corrected model stable, but it actually improves the climatology of stable simulations further, such that instead of all the seeds having very different precipitable water, if you use exactly the same machine learning, but now use the novelty detector to turn off the machine learning when the climate is out of sample in a particular column, the seed zero results for precipitable water, shown in panel C, now get a lot better, while the best results basically stay the way they were before. So basically, the novelty detection is able to reduce the worst climates and make them look a lot more like the best climates, which is reassuring because it makes the machine learning more robust in a good way. So this masked approach gives the best overall climatology that we've got so far. So, the general picture here is that corrective machine learning trained on nudging tendencies can improve forecast skill and the climatology of the things that we cared about most in this project, land surface precipitation and temperature of a coarse-grid climate model by 50%-ish. Further reducing the climatological biases versus our reference seems challenging, but it would be very nice to do. That would sort of be make this into a better emulation approach. And with that in mind, we're exploring some other approaches which the machine learning community has helped to develop in the meanwhile. One of them is called full model emulation, and a few examples are mentioned here, including ForecastNet, on which Mike is working. Mike Pritchard is working. Another approach, another hybrid machine learning approach is called hybrid reservoir computing. And I'd just like to show you a little bit of a scorecard of where some different approaches fit in terms of global emulation. And so that you can see the trade-offs. And so in each of these cases, we have a model type. GSRM is a global storm resolving model. So that's the original 3-kilometer model. You run that with high performance computing with thousands of cores. It's slow, 4,300 seconds per day inference time, stable, makes great weather, makes a climate that we believe we trust, very interpretable, except for the huge data volumes. So we'd give it an A on all categories. However, its speed is terrible, so it gets a C on that. If we were to use a fine grid global climate model with a 25-kilometer grid, this is kind of the finest that we can afford to run there, takes less processors, runs about 10 times as fast, and it's still stable. It doesn't do quite as good a job on climate, it has some biases. It's less interpretable because it's more subgrid processes, and it doesn't do quite as well on weather. Still pretty good, still pretty slow. Now we can turn to our approach, this FE3 GFS plus what we call nudge define. Now we run it on almost a factor of 100 less processors. You can't actually run it any faster because now we're running on the cloud, but still 100 times less effort. It's stable. Takes about a day to train. The weather is not bad. The climate is not bad, and it's quite interpretable. So it kind of gets good scores in all of those areas, but not perfect in any of them. The other hybrid approach, which was Arcomano reservoir computing, is run on an even coarser grid in both the horizontal and the vertical. It actually runs a lot faster on a lot more cores. So it now can do a day of simulation in only 2.5 seconds. trains super fast. That's great. The weather isn't very good because it's so coarse. Its climate, it actually has remarkable climate stability, though. That's a strong point. And it's a little bit complicated to interpret, but is somewhat interpretable too. Then lastly, full model emulation, such as ForecastNet. These are models where the entire atmospheric model is replaced by a machine learning edifice. So there's no more dynamical core and physical parameterizations. Could run these with a grid of about 25 kilometers. Now these are run on GPUs or so-called TPU systems. For the other one I'll talk about, GraphCast, which is based on a graph neural net. These also run very fast, 0.3 seconds per day for ForecastNet and 6 for GraphCast. They're only stable to a point, at least in the published versions. So they're not stable enough to do climate at all. The graph neural net in particular takes a huge long time to train, but training time is not an insuperable problem. They do a good job on weather. At this point, they can't predict climate, and they're highly not interpretable because everything is wrapped into one big ball. You can't even think about things like energy and moisture conservation in grid columns yet. Okay, so there are the that's kind of all the competition that's presently sitting on the scene. And thinking about this then more broadly in terms of global atmospheric model emulation, full model emulation is fabulously fast. It's skillful for weather, hasn't achieved climate accuracy, but it has the chance to benefit from huge ongoing ML advances in other areas because it adopts tools from other parts of ML. The hybrid approach currently works better in terms of climate. It can be made pretty fast. It's harder to train efficiently because of the hybrid nature, but it's a lot more interpretable and therefore easier for climate practitioners to digest. I think the verdict is still out, which of these is actually going to take over the climate community, but my prediction is that within 5 years, we'll see one or the other or both of these approaches being operationalized for weather and climate modeling. And they'll become a part of the mainstream of how we do both of those tasks. Okay, so that's it. Don't think I ran over, so I'd be happy to take questions. And if you want, you can use the chat. I don't know if people have been unmuted.
Sorry, it took me a minute to switch things out. But yes, we will take questions, whether that's through the chat or the raise hand function. Everyone should have the ability to start your video, and we will start with Alex.
Hi, thanks, Chris. That was really interesting. A lot of results there. I'm not really even sure what to ask a question about, but I think just because it came up a few times in some of like the overview slides, this idea of conservation of mass or energy and everything, but it wasn't quite clear to me how that was actually being enforced in the machine learning corrections, because they almost seem like they would be designed to violate that, since they're sort of these fictional terms that you're adding to the evolution equation. So could you explain that a bit?
Okay, well, the way it works is that they're column-wise corrections. And so, for instance, if you think about, for instance, a correction to the moisture field. So if you're making a correction to the moisture tendency at each level, say it's a drying correction, then the physical interpretation is that that is moisture that needs to be, or that the machine learning is removing from the model to make it look more like the target. So where's that moisture going? It goes into precipitation. So you add those moisture increments, the drying increments, and they make an additional amount of precipitation. And the way the conservation is being enforced is that that additional moisture is that additional precipitation is also felt by the land surface. So we add that to the precipitation that's fed to the land surface. Similarly, if we think about heat, yes, the machine learning correction is changing the heat budget of the model. And partly that reflects latent heating, and partly that reflects radiative heating. And we can distinguish the latent and the radiative heating by thinking in terms of moist static energy. So by taking the latent part, the latent heating that's associated with the precipitation correction and removing that. Then the remaining part is due to radiation, and the radiation, basically, if you change the radiative heating, you can think of that as changing the radiative flux that has to get out the top of the atmosphere to balance the energy budget. So implied by the machine learning in each grid column then is a change to the top of atmosphere radiative flux. So the way the heat budget is being balanced is through the top of the atmosphere. There's no guarantee that the radiative flux going out of the top of the atmosphere is right, but you can always compare it to the reference model and see how badly biased it is. So in that sense, it's not that the model has a perfect energy budget or a heat or moisture budget, but it is able to exchange energy and moisture with other components in the correct way, consistently, or with space, in ways that we can then test and compare with our reference model. And that, that's really what we mean by conservation. Conservation simply means that I can write down a conservation principle, say in each grid column, that has to be satisfied and that has to be consistent among all the components of the climate model.
Okay,
I don't know if that helps.
Yeah, that does help. I guess maybe that was something that also I wasn't so sure. So when you go and learn these corrections, you have to learn the correction for all those different fields that are sort of related to each other. Like it's the same model that's learning radiation and moisture corrections.
Well, so the only thing we're learning is we're learning temperature and moisture corrections, and then we do need to learn those together. Partly because as a result of the latent heating being the biggest source of heating in the atmosphere and it being connected with drying, if you make a correction to the moisture, you will inevitably, the machine learning quickly learns it needs to make a correction to the heat budget that basically accounts for the latent heating associated with the drying. But those are the things you're learning. The only other thing we're learning is the radiation fluxes that go into the surface, which we use our fine grid model to predict by themselves. And the reason that we do that is that the nudge simulation that we use for everything else to calculate the nudging tendencies actually has very biased clouds. And so it produces the wrong amount of radiation, long wave and short wave radiation down onto the land surface, and that biases the land surface. And we find it's very helpful to remove those biases. And so we do separate machine learning for that, but that's just machine learning at one level, the surface. So within the interior of the atmosphere, we're only learning two nudging tendencies, and we are learning them in a coupled way, yes.
Okay, thank you, that helps.
Okay.
Does anyone else online or in the room have any questions for Chris? Oh, yes.
Hi, thank you. This is really interesting. So I'm not part of the LEAP program. I actually got a master's from Columbia about 5 years ago. And so I was very interested to come back and see what is being presented in this space. But what really interested me about your particular approach is that you said that you began from a machine learning naive place, which is, maybe similar to where I've been coming from, because all of the research that I've done and a lot of the data analysis I've done is just sort of in the world of regression. Mm-hmm. So I'm curious, when you were selecting machine learning approaches to try and tackle this problem, what were some priorities for you, and how did you go about that? And then with the advances that you said have come about, where would you start now if you were to start over completely?
Right. So I guess first I should say that it isn't just me. If you look, for instance, at the director of LEAP, Pierre Gentine, or the person who introduced me, Mike Pritchard, we in fact all came from a domain science background and learned machine learning as a sort of a second hobby, if you want, or a second career. And we're all continuing to learn about machine learning. And another thing to say is that when I started, there really was not a lot of literature in terms of what machine learning would really be applicable to this problem. There was just a few papers by Mike and Pierre and me, in fact, and a couple of other people, John Venn, for instance, at University of Washington, to direct us in particular directions. And so from my point of view, I did have, and I do have an applied math training, so I also have quite a lot of experience with applied statistics. So I wasn't afraid. In fact, I liked the mathematical side of machine learning. So that didn't make me afraid. In terms of our approach, basically what directed us to do what we did was that we chose to use hybrid machine learning. And basically that is because I'm an incrementalist. I was trying to do the minimum machine learning improvement to a climate model that clearly had the chance to make it better. And this sort of corrective machine learning is an obvious choice there. But if you're doing a hybrid approach, then the most important thing is that your machine learning is not too titchy. It's not, if you give it bad inputs, you don't want it to blow up too easily. And random forest is great for that. It's kind of like the VW bug of machine learning. It's not not very fast, doesn't get up hills very fast, but at least it doesn't, you can fix it when it breaks. And then so then we sort of got more and more ambitious with time. So we went into neural nets. We tried convolutional neural nets, but then the full model emulation kind of came along at the same time with weather forecasting and from people doing fields like vision and image processing. And anyhow, it quickly became apparent that we couldn't ignore that. And so for me right now, I am trying to learn about those fields by collaborating with groups that know more about them. So for instance, we're working on full model emulation with Mike's group at NVIDIA because they have a lot of domain experts on vision transformers and graph neural nets and all the things that underlie modern full model emulators. I'm also excited to collaborate with other groups who are more machine learning experts than I am to learn things that we can then bring into our group's understanding as well. But yeah, so it's kind of a learn by doing type approach right now. But, I think the great thing about machine learning for climate modeling is, it's a very exploratory field and you can't, so you can't go wrong really. You don't expect everything to work. If it doesn't work, it's not a tragedy. You can learn pretty much from your mistakes as well as your successes.
Thank you.
We have a question online if you want to unmute yourself.
Hi, Chris. Thanks for the wonderful talk. I had a question regarding at some point during your talk, you mentioned that the nudging tendencies are very noisy, and in I think one of the examples that you showed that you were able to learn around 10 to 30% of the variance in your nudging tendencies. Mm-hmm. So my question is that do you have an idea of how much of the residual variance that you're not able to learn, how much of that is just some sort of a weather noise versus how much of that may be a limitation of how the column model was set up and what predictors were used to make those predictions.
Yeah, well, there's actually even a third factor, which I guess I would say is the most important here, but it could be considered a limitation. So yeah, so one possibility is, well, in fact, one possibility is that we need more non-locality in time or non-locality in space, right? So people have looked at, well, what happens if you then use adjacent grid columns as well as the grid column that you're using, for instance, to represent the effect of winds blowing stuff into your grid cell from information into your grid cell from an adjacent grid column, or memory effect saying convection is, you know, non-locality in time. I think the non-locality in time probably there's probably more skill in that than non-locality in space, but non-locality in space would help us, we know, with learning momentum a bit better. We just haven't done it yet. Okay. But I would say the other bigger problem here has to do with the fact that we're learning a correction. So if we were learning the entire physics, which we've tried to do, in many ways, it's a harder problem, but it's a smoother problem. But the problem that we have right now is we're trying to learn the difference between the coarsened output from a fine grid model, which actually has a certain amount of smoothness in time and space, and a coarse grid model, which has parameterizations which flip on and off. So that flipping behavior, basically the fact that there are switches and triggers in the coarse resolution physics is a huge headache, because that's very difficult to learn. And, you know, it depends on, it can depend on things other than just the temperature and moisture profiles, but it can depend on, yeah, it can depend on things that are actually difficult for us to figure out, ancillary variables. And so it's because we're trying to learn that difference, I think, that this is so hard. So often, for instance, we see large nudging tendencies where the coarse grid model has put the top of the boundary layer at one height, and the fine grid model sort of has it at a different height, and then you get a dipole of, I don't know. So that kind of thing is very hard to learn. So I would say partly we set ourselves up for failure there. But nevertheless, you know, partly because you can learn the mean of things, and partly because what state-dependent learning we can do is quite helpful. It's still, you know, it still works. It just doesn't work as well as maybe it could.
Thank you. You know,
Yeah.
It's very interesting. Yeah, thanks. Yeah.
Okay, we can take one more question if there's anyone online or in the room. Okay, I think those are all the questions. Chris, thank you so much for joining us and for your talk. Do you have any last thoughts, comments?
No. Well, thanks very much for listening, and good luck with all of your own machine learning ventures.
Thank you.
Great.